Hey there, here's another screencast. This one is on the proof of the p-test for improper integrals. Let me start out by stating the theorem. I'll let you read the statement. This theorem considers the very special case of integrating these monomials in the case that we have an improper integral. So notice in part 2, if my p were negative, then this is not an improper integral. So the only cases where this could be an improper integral is when p is positive. So let's walk through the proof. We're going to prove these one at a time. Hope you followed that. We want to look at this improper integral of type 1. We rewrite it using the definition of an improper integral. So it's a limit of a definite integral, one that we can use the fundamental theorem of calculus on. In this case, we have a monomial, so we can use the power rule to calculate its antiderivative. So the antiderivative in this case, if this were x to the negative p, your new exponent is going to be 1 more, so your new exponent is going to be negative p plus 1. And then you divide by your new exponent. So here, even though p is positive in the denominator, this is the same thing as writing x to the minus p. Then applying the fundamental theorem of calculus, we've got the limits of integration, etc., etc. But if p is 1, then the antiderivative of 1 over x is natural log of x. And so applying the fundamental theorem of calculus, we do that. So continuing on, and you know that the log of 1 is 0, so we'll just get rid of that right now. We'll evaluate the limits of each of these separately. Let's look at the second one. For the second statement, and let's denote that by two asterisks. So I'll use asterisks over here to help us cross-reference. We see the limit diverges, because the natural logarithm is a function that grows without bound. So as its input grows without bound, its output grows without bound, so the second limit diverges. For the first statement, the one with a single asterisk, what do we see? Convergence depends on 1 minus p. So there are two possibilities. Two things can happen. One minus p could be positive, or 1 minus p could be negative. 1 minus p can't be equal to 0, because that's this case. If 1 minus p equals 0, then p equals 1, and we've already covered that. So in the case where p is not equal to 1, only two things can happen. 1 minus p is positive, or 1 minus p is negative. If 1 minus p is positive, then y equals m to the 1 minus p grows without bound as m grows. So the improper integral in that case diverges. If 1 minus p is less than 0, then y equals p y, then y equals m to the 1 minus p is 1 over m to the p minus 1, and p minus 1 is positive, so this converges to 0 as m grows without bound. So the improper integral converges. Oops. Converges. So just to review, what we've shown is that if p equals 1, the limit diverges. If p, or 1 minus p, is bigger than 0, or that is to say p is less than 1, then the improper integral in that case diverges. And in the only case the integral converges is if 1 minus p is less than 0. This shows the integral from 1 to infinity of 1 over x to the p dx converges exactly when 1 minus p is less than 0, i.e. add p to both sides, p is bigger than 1. And that's what we wanted to show, number 1. So that part of the proof is complete. Now we'll consider the second statement. Remember that for this to be an improper integral, p has to be positive. Using the definition of the improper integral, we write this, and here's where we encounter the two possible ways that this expression could anti-differentiate, depending upon whether or not p is 1. So following the calculations almost exactly the way they were in the other case, we get this. Then at the end here, we know that the log of 1 is 0, so I'm just going to drop that. And we'll look at both of these situations separately. So I'm going to call that asterisk 1. I'm going to call this asterisk 2. So consider the second of these. So situation double asterisk. We know the log functions, it's unbounded near 0. So as m goes to 0 from above, the natural log of m is going to negative infinity. So this expression is growing without bound. So therefore we can conclude that the improper integral diverges. So now consider the other situation. The behavior of the limit, or the improper integral, I should say, the behavior of the improper integral depends on the sign of 1 minus p. And there's two things that can happen. Either 1 minus p can be positive or it can be negative. If 1 minus p is negative, then p minus 1 is positive, and m to the 1 minus p is the same as 1 over m to the p minus 1, where this time the exponent is positive, and this expression grows without bound when m approaches 0. And I'll say from above. to keep it all positive. Therefore, in this case, the improper integral diverges. Now in the remaining case, and that's the case of if 1 minus p is positive, what happens there? If 1 minus p is positive, then m to the 1 minus p vanishes as m approaches 0. I'll say again from above. So the improper integral converges. And I'll just emphasize when 1 minus p is bigger than 0, and so that's the same thing as saying when 0 is less than p is less than 1. Pulling in the original assumption that all our p's have to be positive for this theorem even to make sense. And that's it. That's the proof. That's what we set out to prove. We could go one step further and say what the value of the integral is, but that's not what we were shooting for. We just wanted to show convergence. So there you go. I'm done. See you later.